this lecture in which we're gonna analyze boundary value problem but in two dimensions, meaning we will have some kind of a domain. There will be some governing equation which will govern how variables say u, which will in general be a function of x, y and t. But if everything is steady, it will be a function of x and y with some specified condition at the boundary. And in this particular lecture, we're gonna be solving a Poisson equation. In particular, we'll be solving minus Laplacian of u some f of x comma y. But in this particular lecture, since we're gonna do it numerically, why don't we select what f is gonna be, so that rather why don't we select what u is gonna be. Based on that, we'll find out the Laplacian and figure out what the function f has to be. So what we'll do is, let us choose u as, okay, we'll have it x square minus x to the power 4 times y to the power 4 minus y square. So essentially, this particular function is the solution of which equation, where we're doing a back calculation. Okay, if u is this, then the Laplacian of u, and I have the expression in front of me, it is twice 1 minus 6x square times y square times 1 minus y square plus twice 1 minus 6 y square times x square times 1 minus x square. Rather, minus of this is this. Alright, so we can imagine that this is the problem. Okay, so this is the governing equation subjected to, so we have the domain given as a square. This is the origin and the side is 1. Alright, so this equation 1 is subjected to u equal to 0 on all boundaries. And if this is the case, then the solution is given by this. Well, we've taken some form of u and figure out what the governing equation should be. But this is just to eventually match it with the numerical solution. So yeah, that's the problem we have, solving this Poisson equation. So how do we go about solving this Poisson equation? Alright, so first things first, discretization. So we've already covered a one-dimensional problem. So if we have a one-dimensional problem, the boundary value problem consists of conditions at two boundaries, and you discretize the domain like such, like so. And depending on which point you're focusing on, you can write the form of a derivative at I in terms of I plus 1 and I minus 1. Alright, so then what we had was a system of equations which resembled something like this, and the solution was found by doing an inversion of A, and we used the sparse solver of SciPy to get our job done. Alright, and how did the matrix A look like? Well, we recall that it was a tridiagonal matrix except for the boundaries. So if there was a second derivative, there was some diagonal value like 2 and then the off diagonal value was minus 1, then it was 2, minus 1, and so on. Okay, so it was a tridiagonal system. But what about systems in two dimensions? Well, things start becoming slightly more complicated, and we will have a pentadiagonal matrix. But why is that? Let us see. We have a domain like this, which is divided into many parts. Essentially, we have a mesh grid, right? So when we do have a mesh grid, we have to number this. So let us number the columns by I and the rows by j. And this is customary because of I'll show you why it is customary. So if we focus our attention at this point, let me zoom in. So this is what we have. This is I comma j, and the location I comma j corresponds to some location xi, which will be I times delta x, and yj, which will be j times delta y. But delta x and delta y are these grid spacings. Alright, so now if this is ij, this particular thing will be I plus 1 j, this will be I minus 1 j, this will be I j minus 1, this will be I j plus 1. So that's how the grid points are. So let us write down the Laplacian in the discrete form. So the Laplacian of u at ij will be del to u del x2 plus del to u del y2 evaluated at I comma j. This particular term will be, well, we can directly write this down because in one of the previous classes we have written down what the expression for this particular term should be in the case of an ordinary differential equation. Well, we'll have u I plus 1 j minus 2 u I j plus u I minus 1 j upon delta x square, and this particular term will give us plus u I j plus 1 minus 2 u I j plus u I j minus 1 upon delta y square. Let us recall what the equation is. So it's minus of Laplacian of u is equal to this function, whatever it is. Alright, so minus of the Laplacian of u at I comma j will therefore be 1 upon, so let us assume that delta x and delta y are equal. And it's not a very bad assumption. But anyway, if you do have the case where they will be different, you can easily modify whatever I'm going to show without much difficulty. But for now, it serves our purpose to do this particular assumption. So let us assume that it is equal to h. So 1 by h square times, so there's a minus sign over here, so you multiply everything by minus 1, so we will have u I j minus 1, another minus of that, minus u I minus 1 j plus 4 u I j minus u I plus 1 j minus u I j plus 1. This is what we have. But now, in the case of one dimension, in the case of a one-dimensional problem, if we have n nodes, okay, so if the number of nodes are n, then the number of unknowns, depending on, so suppose we have Dirichlet boundary condition at the boundaries, then the number of unknowns will be n minus 2 if there are n nodes. Or what about in the case of a two-dimensional problem? So if all the boundaries have a Dirichlet boundary condition, then the number of unknowns will be all the inside grid points. It will be n minus 2 whole square, right? So those will be the unknowns, but rather than just focusing on the interior grids, we will let there be n square number of grid points. So if there are n square number of unknowns, if we were to arrive at an equation which would look something like this, the size of the matrix A has to be n square by n square, which is in contrast to the case of a one-dimensional problem where the size of the matrix A was only n by n. And this n square by n square arises solely because we have n square number of unknowns, that is all the grid points. So if I were to focus on this, let me just draw the grid again. I have at ij point contribution from this point, this point, this point, and this point. That is from all the nearest neighbors. Alright, so we have contributions from all the nearest neighbors. So suppose I'm focusing my attention on, well, okay, let me write this. Let me take only a few grid points. Something like this. So if I write down the equation for this point, I will have contribution of these 4 points. If I write an equation for this point, I will have contribution from these 4 points. I'm not discussing about writing an equation for this point or this point because they're at the boundary. If it's a Dirichlet boundary condition, the conditions over there will be automatically defined. I don't have to worry about them anymore. So what about this point? We will make use of what is known as linear indexing. And linear indexing is useful for us to represent a pair ij as a simple linear index. So this point becomes 0, this point is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the linear indices of all the variables. So in the end, we will have a times x is equal to b, where x is the value of the variable. So x is essentially u, alright? X, I mean, I'm calling it x, essentially it's u. So then what will be u? U will be this thing, u0, u1, u2, all the way to u14, u15. Alright, so there are 16 elements over here. So u is 16 cross 1, a is 16 cross 16. As I've explained, it's going to be n square by n square, and b is going to be 16 cross 1. So now let us focus on 5, u5. So when I'm writing down the equation for u5, alright, so there will be u3, u4, u5, and so on. So what about the equation for u5? u0, u1, u2, u3, u4, u5, u6, and so on. So u5 will have contributions from u4, u6, u9, and u1 because these are the nearest neighbors of 5. Alright, so in terms of the linear index, what are the contributions? It's the linear index -1 +1 plus n, where n is the size number of grid points in one direction. So this is what, 5 plus 4, this is 5 minus 4. So it's the linear index plus n and linear index minus n, right? So the matrix A will resemble something like this. So it will be what? So what do we have? We have 1, right? So 0, -1, 0, 0. So there will be a -1, 4, -1, 0, 0, -1. So this is what? This is gonna multiply, sorry, and so on, and it's gonna multiply u0, u1, u2, u3, u4, u5, and so on. So this is gonna be the row of which this particular element will multiply u5, because we are focusing on u5. So 0, 1, 2, 3, 4, 5. Excellent. This is gonna be this. If this multiplies u5, this is gonna multiply u4. This is gonna multiply u6. So these are the x nearest neighbors. This is the nearest neighbor from the south, and this is the nearest neighbor from the north. All right. So all of this is which number of row is this? This is gonna be the sixth row. All this, everything else is 0. So all this is the sixth row. It's going to multiply such that this 4 multiplies with u5. Think about it, right? Well, like I've said many times, this is not a course where we're going to discuss all this, but hey, in case you know all this, I'm just giving a quick refresher. In case you're not aware, I'll post some links, you can have a look. But it should be clear that there are n square number of elements. Apart from the nearest neighbors in the x direction, you also have the nearest neighbor contributions from the north and the south. And because of the shift in the linear index by n, so there will be from this position, from the position of the prime importance, that is ij. So this is the linear index corresponding to, so this corresponds to the linear index 5, right? So the nearest neighbor from the north and south will have a shift of n, where n is the number of grid points. All right, so with this in mind, let us start programming, and as we go in the program, we will discuss various aspects of it. All right, so let me go over here. Oops, so let me create a new file. So the purpose of this function is to solve a Poisson equation in 2D, and the Poisson equation under consideration has already been mentioned in the notebook, but yeah. So first things first, we're gonna define the number of grid points in the x and y direction. So let us say nx is equal to ny is equal to, say, 5, only 5 grid points, and the corresponding h. So h is gonna be what? Alright, so if you have 5 grid points from 0 to 1, then the grid size is gonna be 1 upon n minus 1. Alright, so let's do that. H is gonna be 1 upon nx minus 1. Alright, so far so good. So let us predefine, or before all this, I've forgotten to add the different packages that we will need. In fact, we don't need ipy widgets. In fact, we're gonna import scipy dot sparse as scs, and from scipy dot sparse dot linalg we're gonna import spsolve, right? So far we have defined what nx and y are and what h is, and now based on this let us predefine what a and b are going to be. So a is going to be np dot zeros, and it's going to have nx square comma nx square. Well, actually it has to be nx ny square cross nx square, but nx and ny's are they're equal, but still for completeness I'm going to make this ny square by nx square. All right, b is going to be np dot zeros, and this is going to be nx square comma 1, or it's going to be actually nx cross ny comma 1, but anyway they're equal, so it doesn't make a difference. And similarly x is also going to be, or let me call it u, it's going to be np dot zeros nx square comma 1. All right, so far so good, nothing wrong. So what we have done so far is we've simply defined all the different matrices, arrays that we're going to use, nothing fancy. So yeah, let us do a loop for j in np dot. Okay, so let us only focus on arriving at the inner points. So what we're gonna do is we're gonna disregard the I equal to 0. So I equal to 0 corresponds to this, I equal to n minus 1 corresponds to this, j equal to 0 corresponds to this, j equal to n minus 1 corresponds to this. So what we can do initially, so we can disregard all those boundary points. So we can simply do a loop over the inner points. So I for j equal to np dot a range 1 to nx minus 1, for I in np dot a range 1 to so this has to be ny minus 1, and this has to be nx minus 1. So now what are we going to do? So first we will define L as the linear index. So what is L? So if you look at this thing, so the linear index L will be equal to I plus j times n, right, where n is the number of points in this direction. They're equal, so it doesn't make a difference. So let us see. So for this point, I is equal to 2, j equal to 1. So the linear index is 2 plus 1 times 4, which is 6. And this the linear index is actually 6. So good. So the linear index is I plus j minus this is what linear index L is I plus j times n. Great. So once we have the linear index, we have to then construct the matrix, this particular matrix. So the diagonal element is going to be 4. So a l comma l, that is the diagonal element, it's going to be 4. A l comma l minus 1, it's going to be the neighbor on the west, it's going to be minus 1. A l comma l plus 1 is going to be 1, that's the neighbor from the east. A l comma l minus nx is going to be minus 1, that's the neighbor from the south. And this is going to be l comma l plus nx, and that's going to be the neighbor from the north. All right, so far we've just constructed the matrix A. Let us print it out. All right, so n is not defined. Okay, this has to be nx. All right. Okay, so we have a lot of things. Let me make it 4. All right, so look at this. So we do have the pentadiagonal matrix system. So this, and this. So let us see. This is done for 4. So what we have over here is 4. So this is what 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So for the element with the linear index 5, we do have 4 internal points. So let us see. 0, 1, 2, 3, 4, 5. Right. Oops. So 0, 1, 2, 3, 4, 5. Okay. So the diagonal element checks out. Then for 6 also we do have the nearest neighbors. So this is for 6. Then for 9 we do have a nearest neighbor. So if this is 6, 7, 8, 9. So 9 also checks out. You can verify this column number is also going to be 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so everything checks out. So we know that the code is correct as far as internal node generation is concerned. Right? So what we can do is now extend our code so that we're not restricted to only the inner nodes. We want to account for all the nodes. But what we are going to do is make a check. So if I is not equal to 0 and j is not equal to 0 and I is not equal to nx minus 1 and j is not equal to ny minus 1. So what this means is if you are not at the outer boundaries, then you do this particular assignment, right? So then you do this particular assignment, else you do something else, right? So this should do nothing. I mean, else you do nothing. Okay, I need to, let me just remove this. So it still gets the same output. So now what we need to do is inside this, we need to put in the boundary conditions. So if this is not satisfied, else, so this else statement means we are at the boundary. And at the boundary, u is equal to 0. Meaning u0 is 0, u1 is 0, u2 is 0, u3 is 0. So all these linear indices correspond to j equal to 0. Alright. So what I mean to say is the linear index corresponding to these boundaries have the Dirichlet condition that u0 is 0, u1 is 0. So simply this will imply a l comma l is equal to 1 and the RHS will be equal to 0, meaning how will the matrix look? So u0 0 is 0. So 1 0 0 0 0 all zeros, 0 1 0 0 0 0 all zeros, 0 0. So 1 times u0 is equal to 0. So the first linear equation that we get from this is u0 equal to 0. From this 0 times u0 plus 1 times u1, so you will have u1 equal to 0. So it's as simple as that. You need to just assign u linear index comma linear index equal to 1. That's it. So now we are at the boundary. Alright, so now we have put in the boundary conditions as well. Or we have forgotten to create the right hand side matrix. By right hand side matrix, I mean this matrix B. So what is B? So we've just gone ahead with the discretization of, we've just written this inside A. So what we have is minus of the Laplacian of u is equal to whatever function was there. So then minus 1 by h square times contents of A times u is equal to whatever we have. So this minus sign we had absorbed into the Laplacian. So h square goes over here. So f times h square is what we have to put in B. So A times U equal to B, where B is gonna be F times H square. Alright, so H we've already defined. What is F? What is F gonna be? F is this. So what we will do is create a function. So BL comma 1 0 lth row 0th column, because it's a column vector, is gonna be get B, and we're gonna pass I comma j comma h. The reason I'm passing only ij and h, because from ij and h we can find out what x and y are, and given what x and y are, we can find out that complicated looking function. It's quite easy. So let me go over here and let me define get B, and the inputs will be I comma j comma h. So x will be I times h, y will be j times h, and then r will be equal to twice 1 minus 6 x square times y square times 1 minus y square plus 2 times 1 minus 6 times y square times x square times 1 minus x square. Alright, so we must return r. That's it. That's pretty much it. So we have to assign B this value of the RHS. Okay, so far so good. Over at the Dirichlet boundary conditions, we don't have to do anything because as such B has been initialized to 0. So unless it's something non-zero, we don't really have to worry about it. Alright, so let me run this and see if something is broken. No, everything runs just fine. So what do we have? So we have constructed the matrix A and matrix B. So let me convert A to a sparse matrix, and the reason we want to convert A to a sparse matrix is because we want to use the sparse solver. The sparse solver is usually much faster than a dense solver. It requires much less energy, right? Not energy, it requires much less RAM. You don't have to store all the elements. Right? So convert A into sparse. So CSR format. So compressed storage row format. And so A will be SCS dot CSR matrix of A. B will be SCS dot CSR matrix of B. And finally, U will be SP solve A comma B. Boom, everything runs. Great. So now, now what? Let us print U and see what we have. So U has some values. We don't know whether it's correct or not. But how do we know whether it's correct? We know whether it's correct or not because we had assumed the solution in the first place. Right? So we do have a way of ascertaining whether whatever we have written it's correct or not. So let us define this. Let me define exact at I comma j comma h. So it will have this. The r will be equal to x square minus x to the power 4 times y to the power 4 minus y square. Alright, we must return r, and the reason why I'm returning it is, I mean, what I can do is, I mean, there's multiple ways of doing it anyway. So let me first reshape. Okay, let me define xi and yi as linspace 0 to 1 having nx size. Alright, so now xi comma yi will be np dot mesh grid xi comma yi. Now what I will do is I will reshape the solution u. So remember, a is now a linear index, so if I were to traverse that particular linear index, I would traverse something like this. Okay, so I'm traversing it like this, but I want to reshape it to a square matrix. So what I will do is u equal to np dot reshape u comma nx comma ny, or rather it should be ny comma nx. I mean, it doesn't matter because they're the same. So we have reshaped. Now let us do a plot. So plt dot plot, not plot, contour xi comma yi comma u. Yeah, let's see how it looks. Okay, looks weird. Maybe because we have very less points. Let me take 20 points. Okay, so we must reshape. Not hmm. Ah, we had made one fatal mistake. Okay, yeah, this looks much more like it. I was wondering the solution doesn't look right. Okay, anyway, there was a small mistake over here. I'd written +1 instead of -1. Such things happen when you're doing it all out. But anyway, but how do we know this is correct? I mean, you need to also plot the exact solution, right? So let us do that. xa equal to ya equal to np dot linspace, or in fact xi and yi, let me just define it. Xa equal to ya equal to np dot linspace 0 to 1 100, xa ya equal to np dot mesh grid xa ya, then u analytical will be simply x a square minus x a to the power 4 times y a to the power 4 minus y a square. So then we'll also do plt dot contour x a y a u a color map or c map equal to jet. All right, let's okay. So there are two color maps. One is the jet and this, and they do appear to be quite close. If I take a larger number of points, maybe 50, they seem close but not exact. They should be exactly the same. Maybe I've gotten some term wrong somewhere. Let's see. We don't need this. Well, maybe they are correct. Let me just resample this to 50. No. Ah, I know what's wrong. I forgot to multiply this by its square. This is a very small mistake. In fact, spoke about that but forgot to implement it. This particular h square that comes from the discretization of the Laplacian. I forgot to write it down. Well, now everything should match quite well, and there you go. Everything matches quite well. And you can go ahead and take a loop over all the points and find out the maximum error. I'm not going to do it over here. Let me just show you what happens when you reduce the resolution. It looks qualitatively the same. Once you start taking higher number of points, maybe just 20, it resembles it quite well. With just 30 points, it converges quite nicely. So what I request you to do is to find out how the maximum error changes as the number of grid points increases. So to conclude, in this particular lecture, we have looked at how we can discretize a two-dimensional system. We have seen that we end up with a pentadiagonal matrix. We can do a sparse solution of that matrix. We can find out the solution. And in this particular synthetic problem, we have sort of compared the solution against the analytical solution. And they do turn out to be quite well once you have a larger number of grid points. So with this strategy, you can pretty much implement any boundary condition you have. You can use the ghost node strategy to implement the Neumann boundary conditions as well. I have not discussed it over here, but it is a straightforward extension of what we had done for the one-dimensional case a few lectures ago. So with this, I am gonna end this particular lecture and this week. Next week, we're gonna start with PET C, and I'll see you then. Until then, goodbye.